Yeah, that's good. That's good. That's good. I feel like you don't actually need to learn what they are to know how they work, but
That's fair, yes.
you don't need to build it.
Yeah.
You don't have anyone online today? Okay, that's
Yeah.
interesting. Am I in the right meeting?
Yeah.
Maybe I did.
I know. How many did you have? You have six. Every, I have a problem with six.
Okay, all right, you all watch the videos, right?
Let's take a quiz.
I don't know if it's gonna work. This is the first time I'm trying this. So if you have a laptop, the URL is there, which is a pain. If you don't, you can do this on your phone. It's a Google form. It shouldn't be super hard. It's mostly, did you watch the thing and are you awake? This is bonus. You'll get some points for taking it, and you'll get some points for how many you get right. But I want to just give a little, I don't know, opportunity to just sort of rehash some of the things that we should have had in the video if we did watch it. Okay, is everyone able to get in? There's at least some people able to get into the quiz. Put your email in there. Please use your Purdue email so I can look at who you are. Okay, not some other random email. Because I need to link it to whatever is in Brightspace. So please do that. And I think with this, I can like look at live results here of how you guys are answering this. Shouldn't take more than a couple of minutes. Do your best. If anyone still needs the QR code or website, let me know. I'll try and put it back up. You can still take it. Hold on. Trying to make it so you can't see the answers, but you can see the live results. Let's see. Okay, here we go. Maybe I can do this. Here. Okay, so if you're joining us now, try to get that QR code. These are your live scores. We have 12 done. Again, if you don't do super well, it's not the end of the world, but maybe an indication that you didn't either watch the videos at all or super well. Use your Purdue email also for the new person who just showed up.
Yeah. So, right, just guess recently. So,
Guessing, since they're all two options, is 45.5.
Better than after it's. Better than guessing. Yeah. They'll, if it's a couple. Is it the Ainsley thing?
Yeah.
They said they'd be there like after. They hang on the squash.
Yeah, they should be there. I just met with them for other reasons, but yeah, they should be there. Yeah. So you don't have to skip class and go to the AD. Yeah, there's most people are well done. Okay, nobody has gotten worse than Chance, so that's a good sign. It gets weird. We just have just one not done. Are you done now? Who is not done? Do not be afraid to raise your hand. Okay. Everyone is done? Now they are. Okay, I think we have about that. I may have miscounted. Closer. All right, so generally you guys seem to do relatively okay here. Let's see. I don't know that I can get them anonymized easily here. Oh, do you get to see your scores?
Yeah.
Oh, you do? Okay, I don't have to push this. Okay. Let's see. Let's see how people did generally. What does it show me here? Oh, no. That's not what I wanted. Individual.
You can look at the.
No. You guys know? Does anyone know how?
That'll go question by question.
Okay.
You can just read through the questions. Try to see.
You want to see the? Well, can I see which ones you did poorly on? Who's done this before?
I think it's a summary.
Yeah, is there a summary? Summary, the problem is there's lots of emails and scores on here. Maybe if I go real fast, here we go. Not that it matters. Okay, it doesn't matter what you got. All right, so the first one, okay, mostly yes, except for one. Second one, you mostly got right, maybe 3. Let's see, which one is the worst one? Oh, okay. Okay, that's interesting. So an even tie between question, whatever this is, and then the last one. Still more people got it right there. Okay. The last two then. Who got the second last question right? Who got the last question right without guessing? Okay, who wants to explain why it's no and not yes? Any brave souls? You look like you want to answer.
I guess it's because registers are treated with that. Yeah, so like it doesn't matter because every register, like every third has a register. Doesn't matter.
Right. So the registers that are used by a warp, right? These are assigned to compile flags. Okay, and the way that they get assigned is like a whole, you can't just do part of a register in the allocation of registers for warps. So even if your code is going in these weird directions, right, and then some threads aren't actually using some of those registers, it doesn't matter. It doesn't actually affect it. You still are allocated that register space. It's just essentially wasted. Okay, so even if your code has this control flow divergence where, you know, half of them go down the if path and they use register 16 and the other half go down the else path and they use register 32, you still allocated a register for everyone who didn't go down the other path. It doesn't actually change your allocation because this is sort of done statically. So that's why the answer to that one is no. Oh, there's some late bloomers that came in here just waiting for the answers and then it, or maybe not, because it was even, right? Now it's not even. So anyway, I don't care. And the last one, okay, this one sort of ties directly to a question that was in the lecture, right? That was online. So if you watched that, you sort of got it. Who wants to explain this one? Okay, why the answer here is no and not yes. Yep.
Because in this example, we have 124 thread block size and 32 warp size. So we essentially have 32 warps.
Right.
And then in that condition, it's basically saying that the first 16 warps will go true, and then the last 16 warps will go false. It's right along that.
Exactly. So since I'm dividing the thread IDX by the warp size, that effectively gives me my warp identifier. So I'm not going to have partial warps. I'm not going to have part of a warp go x plus 1 and part of a warp go x minus 1. They're either all going to do it together, or they're all going to do it together whichever way they go, right? They're either all the threads in the warp are either going to do +1 or they're going to do -1. There's no warp that's partially going one way and partially going another, okay? And that's because I've sort of used this, and this IDX is an integer, right? So then it ends up basically everything less than 32, every ID less than 32 will basically be 0, right? And then everything 32 to 63 will end up with 1, and this will basically be the identifier for the particular warp. So what you will get here is, you know, something you could call warp divergence, meaning that the different warps will go down different paths. But that's actually fine from the perspective of efficiency, because as long as everyone in the same warp goes together, you're not really wasting resources, okay? So this is actually not bad code for a GPU because all of the warps will go together. All of the threads in a warp, wherever they go, their peer warps will go down different paths, but you know, that's okay. Oh man, I yanked this over here. Give me 1 second. Any questions on this quiz or this sort of answers to these questions here? Hopefully this was relatively straightforward, okay? And I'm guessing that many people who didn't do super well maybe didn't watch the videos or didn't watch them as closely as maybe you could have. Okay. Questions? All right. Give me a second to bring this thing back up for the recording. Was this useful? To at least think about it at the start of class? Okay. The Google form thing is kind of, I'll try and use it again. Let me just quickly do something here. Okay. All right, so what we're going to do now is I'm going to not go through each of these lectures that I asked you to watch in detail because you watched the video, but I asked you all to come up with some questions, okay, on each of and you know, the idea here is that maybe you can get a deeper question than if you've just sort of seen it for the first time. So what I'm going to do to sort of facilitate questions that you have is go through, let's see, where am I at here? So we did all this. I'm just going to give you a spin through of what was in that particular lecture, and then I'm going to solicit questions from you. Okay. So like, I'm not going to fully go through it. I'm just going to be like, okay, this is what this was about. Who has questions on that particular piece? And everyone should be able to raise their hand if you sort of did your assignment here. All right, occupancy. So the first thing I asked you to look at was this occupancy thing. Okay, this was the first video, right? And we talked about, you know, we ended lecture here. We talked about assigning thread blocks. to an SM. We talked about different factors that limit your occupancy. We went over a couple of older architectures in the video to tell you the kinds of resources that they have. Things change every generation. There were some quizzes in, I don't know that they're actually in the vid. Are they actually in the video, or we just make you do these on Brightspace? Is the answer to this in the video? Do you remember? I think we skipped it. So the Brightspace quizzes will give you these questions, okay? And they're really centered around trying to figure out, based on, how you cut up your parallelism, how much occupancy you're going to get on your GPU on average, okay? Any questions on occupancy in general, or how you solve these problems? Nothing? Yes, right.
So, I went to the lecture and then, I understand what is warp and what is dreadlocks.
Yeah.
I'm not getting an insight on why we need to group a couple of warps into dreadlocks. So what is the purpose of the dreadlock?
So the purpose of the thread lock from a hardware perspective is sort of meaningless, because a warp is a warp and it's something I can independently schedule. From the purpose of a programmer, I can do things across a thread block that I cannot do if they're not in the same thread block. Okay, so I can basically share the scratchpad memory that we'll talk about probably today. I can do fast synchronization among the warps in a thread block. And when I said that the hardware doesn't care about thread blocks, that's not true. The individual cycle level issue scheduler doesn't care about thread blocks. But there's an allocation mechanism to assign work to a core. And that allocation mechanism does that at the thread block granularity. Okay.
So the scratchpad is written to an SM, right?
Correct. The scratchpad is within one SM.
So again, without a dreadlock, let's say, single dreadlock has only one warp.
Yeah.
Then I don't still get how the scratchpad comes into the picture when we have dreadlock.
So if a thread block has only one warp, it's sort of meaningless in a lot of ways, because you're not sharing anything. You don't need to synchronize.
We can still assign multiple dreadlocks.
You can, but okay, so within a thread block, you do not have the flexibility to take one warp in the same thread block and put it on another core. Okay? If I have multiple thread blocks, I can assign them to different cores, because their resources, their shared memory usage, their synchronization mechanisms are separated. So I think that, does that sort of answer your question? Like, if it's just one warp, then I can spray the warps across all of the SMs in any order I like. If I just have a thread block that's one warp wide. If my thread block is 32 warps wide, so a 1024 wide thread block, I have to schedule all 32 of those warps on one core together. And if I don't have room, so I've got space on that core, let's say for 756 threads, and my thread block is 1024, then I just cannot schedule it, and it has to be serialized.
So this dreadlock actually limits the flexibility.
Exactly. So there's a trade-off here. The bigger the thread block is, the less flexible your scheduling algorithm can be. But the bigger your thread block is, the more opportunities you have for tiling, the less, the more, basically the community, the more stuff that you put together, the more threads you put together in that block, usually the bigger the tile size is when you start to tile the algorithm. That's really the big upside of doing that. And you also only have a finite number of thread blocks you can assign to each core. So if you made them super small, then you'll run out of number of thread blocks you can have in a core, and you still won't get maximum occupancy. So typically what we'll want to do is right size the thread block, which is usually as big as we can get it without hurting occupancy, because we're able to sort of share locality across those threads in the scratchpad. That's the general win. Does that make sense? This will become a lot more clear as what we're going to do next is talk about optimizing matrix multiplication, or general matrix multiplication algorithm, through using the shared memory, through blocking it, and it'll become a bit more apparent why this is so advantageous to make the thread block bigger. Okay, yeah.
Is the compute resources that's like available in an SM equal to like the largest amount you can make a thread block, like how big you can make a thread block, or is that like different?
It depends. It's architecture dependent. Historically, it's usually been about half. So that thread blocks can be half as big as an SM. So you usually put 2 thread blocks on, but this is just architecture dependent. Okay, other questions. And so you have to, so I mentioned that we want the code to sort of be like implementation independent, so it doesn't matter what, architecture you're running on. But when you're doing these kind of fine tunings to maximize occupancy, you do have to have some awareness of what architecture you're running on. When you run these ML libraries, like cuDNN, what have you, behind PyTorch, there is stuff going on to try to right size your thread blocks to whatever machine you're actually trying to run it on. There's system software that's trying to do that for you. But as a CUDA programmer, you're sort of forced to do that yourself. Okay, good question. Other questions? Yep, right here.
So if you use like very small thread block sizes, is there like significant overhead in scheduling them?
In the spawning,
Yeah.
not especially. It's pretty cheap to spawn. Now there is overhead, right? You do have some latency. If they're short running and there's a bazillion of them, then you're going to spend more time spawning. But we've measured this, and in practice, it's really not that big a deal. Yeah, but there is some overhead, obviously. Yeah.
So if you have maximum occupancy,
Yep.
why is it you're not guaranteed necessarily the fastest completion time for a given workload?
Right. So because occupancy is only looking at one of those metrics. Okay, so there are 4 things that could limit the amount of work you get on each core. Occupancy is looking at which one? When I say occupancy, you can measure the occupancy. Run a kernel, it'll tell you had an 80% average occupancy in this machine. What is that measuring? Number of threads. Okay, so if I packed all of my context full, so every SM had the maximum number of threads in it, I've got 100% occupancy. You almost never get exactly 100% because at the end of the program, they start to tail off and it doesn't average across all of the time, right? So, but that's only measuring that one metric. It's just measuring threads. It turns out that sometimes you're better off having less threads where each thread does more work, okay? And the impact, what do you think the impact is of having each thread do more work? Which of those resources are you going to consume more of if each individual thread would do more work intuitively? Sorry. Heard a mutter. Registers. Why registers?
Most, yeah, it mostly gets them, but then it mostly gets, but if each thread is taking long to run, then those registers won't be free as often.
Sort of, but your information on registers is right. Like usually if you pack more work into one thread, the compiler can unroll loops, right? It'll make it try to make the code more efficient. Those unrolled loops take more registers, or just generally, it'll do optimizations within the compiler that consume additional registers to do that extra work. So what ends up happening in a lot of optimized kernels, and we see this in machine learning, most of the kernels that run when you're training GPT, well, you're not training it, but whoever is training it is doing it, they're not running with 100% thread occupancy. They're actually quite low. The occupancy is somewhere around 20%, but the register usage is 100%. So they've crafted those individual kernels to soak up more registers to basically do essentially like something like register caching, right? So you have locality you can exploit in the Scratchpad, but you also have a lot of locality you can exploit in that giant register file. And if you can give the compiler the information to do better register transformations by packing more work in, it's usually better than splitting it across parallelism-wise. So when we're sort of telling you how to write a CUDA program, very first thing you want to look at is just like scale it up so I use all the threads. Then once you sort of scaled it up to use all the threads, then you look at the work each individual thread is doing, and then try to see, is there a more efficient way that I can sort of pack more work in to try to usually soak up register usage. Okay, good question. Does that make sense? So it's not like you're not using the machine. If occupancy is low, you're still actually using all of the registers in the machine. You probably have better register efficiency than when you used all of the threads because you probably had registers left over. And your execution units are still kept busy because each individual thread is probably stalling a little bit less because they're making better use of registers. So if you just looked at utilization in terms of how often are all of my AOUs doing useful work, it's going to be higher even if you have less threads assigned to the cores, if each of those threads are doing work in a more efficient way with more registers. Okay, so that's why that answer to that question was no. Like it's not a max, like just maximizing parallelism is not necessarily going to maximize the performance of your workload. Okay, and again, you kind of have to play with that trade-off when you're optimizing your program. Okay, good question. Other questions on occupancy? Yeah.
Doesn't that kind of go against like what people say, which single thread performance is really bad on GPUs? So what, like, why do people say that?
So single thread performance is really bad on GPUs relative to CPUs. Okay. Single thread okay. So what can make single thread performance bad? Low frequency. Okay. In order execution. Okay. No register renaming, no dependency. Basically, you have to stall on any dependencies, etc. Okay. All of which the GPU has relative to a CPU. Lower frequency, yes. No out of order execution, no register renaming, all this sort of no prediction, right? The stuff that you're feeding the CPU to get ILP with is just not there. But what the GPU is concerned with is on any given cycle, do I have a work I can issue? Okay. Because they have many ALUs, right? So if I can keep those ALUs busy with more work from one warp, that's the same as keeping it busy with more work from other warps. Roughly, right? Except you're probably getting better register efficiency. So you can sort of think of it like, yes, if I tried to run that one thread by itself and compare that with whatever's going on in the CPU, it's going to be provably slower by a order of magnitude-ish, right? But if I'm running still many threads, and I mean, I have, you could in theory unroll a whole CPU program into one thread, right? You could take the whole GPU program and maybe put it in one thread. And as long as there's enough independent work to keep all of your pipelines busy, your GPU is still going to be happy. The only reason it needs the multiple threads is if there's not enough independent work in one of those works. Okay, so it's a balance between like, where am I getting my parallelism from? Is it from, you can still have ILP in a GPU program, but that's going to be explicitly encoded by the compiler. You need to give me a bunch of instructions that are independent so I can keep issuing them without stalling. Does that make sense? Okay, other questions? All right, so who's taking the quiz on occupancy? Probably some of you. It's not due. Was it due already? No, okay. All right. Is there a question or you're just raising your hand? Okay, so occupancy is something you have to deal with. Again, it changes generation to generation. So then we talked about in the video a little bit on hardware scheduling. Okay, we talked, basically that the programming model gives you this level of data level parallelism. And, you can actually capture this in multiple ways. You can do it on vector units, or you could just put it in different threads. And that's essentially what a GPU does, right? You just have this work that you define with thread IDs, and then it sort of transparently makes little warps for you that run on vector units, but then it makes many of those little warps that it then time slices between, okay? And, I talked about this principle of fine-grained multi-threading, and I think this is 565 stuff, right? You guys still talk about this in 565, at least to some extent, about how you need less ILP in each individual thread if you've got enough threads to cover the latency, right? So this sort of step graph of like, am I always doing useful compute if I can overlap that compute with, or if I can overlap the slowness of memory with the amount of compute I have, I can tolerate long levels of memory latency. And, this is sort of classic CPU example. We talk a little bit about the different kinds of multi-threading. This is a graph you probably also saw in 565, I hope. It's in the textbook now too. This is roughly what GPUs do. It's not precisely, but it's the most similar to what GPUs are doing. To sort of give you some intuition, right? Like in a CPU, if you've got true SMT or you've got truly MIMD execution, each of these columns here could do completely independent work. That's not true in a GPU, right? They have to do actually the same instruction. But the manner in which they sort of switch between each warp is this fine-grained multi-threading. Okay, so like on one cycle, your vector unit's going to do one instruction. On the next cycle, your vector unit's going to do another instruction. Okay, and most of you got this right about the fact it's not actually doing hyper-threading. Because hyper-threading is like another step more aggressive, right? Where on the same cycle, I'm going to issue stuff from different threads to different pipelines. Super cool idea, and actually pretty cheap to implement, but you don't really need it on a GPU, and you don't want to take your SIMDs and make them do SMT, because then you're losing the efficiency of doing it in a SIMD fashion in the first place. Okay, so yeah, questions on this? Yeah, up here. Go one more time. Unfilled slot. Yep. If you just don't have enough parallelism in each thread. This is a toy example, right? Where I'm showing you, I guess, how many colors are on here? 4.
Explain that register allocation, you ran out of registers. For that example.
For that, so the question I think precisely is like, why does, let me just make sure we're all on the same page. Give me 1 second here. Question was like, why is this business here, right, in multi-threading or in macro threading? And your answer was run on PRF.
You said it was because you ran out of registers. It's your classes 5.
Sorry, the professor said this.
Professor.
Did it already say? You run it. Okay, so running out of registers could be one reason why this happens. You also just may not have. You also may not have enough independent work in that cycle, right? There's many reasons why you might have a bubble, right? So basically, I've got 4 in the first 2 cycles. I've got 4 colors active. Okay, what that represents is 4 different, completely different threads of execution. Completely different opcodes, potentially completely different stuff going on, and I get to issue them. So I issued, 2 from red, 3 from green, and 3 from blue in those 2 cycles. On the next cycle, if I don't have, like, if there's a dependency, so basically I'm not doing anything from blue, right? So it could be that blue is stalled, and I don't actually have, my instruction window is not big enough to actually capture some new independent work. Or the branch predictor failed, and I'm not able to keep going, kind of thing. You could be running out of physical registers. There are many reasons why this might happen. So if you run out of PRF, then essentially you can't rename, so you have to stall, because you can't, effectively rename the new incoming instructions. So any reason why a single thread might stall in an out of order processor is a reason why you might have a hole in your SMT execution. And PRF is one of them. Not enough independent work. Your iCache missed, maybe, right? You can't feed that thread for some reason. Those are all reasons why you might have those problems. Does that make sense? Now, if I had enough threads, right? If I'm like GPU scale and I only have 4 here, but let's say I had 8 or 20, right? Then the chances of you not having any thread that can't do anything go down. But again, if you want 20 threads, you need 20 times the PRF, or else you're just going to split it and they're all going to stall more frequently. So there's those kind of trade-offs. That's a really good question. Okay, other question. Yep.
Is it fair to say that fine-grained multi-threading is an example of simile hardware and simultaneous multi-threading?
No, no, it is not. And that is why this is a somewhat deceiving diagram, because this diagram was created with CPUs in mind and not really vector units in mind. So here's the difference. So the Sun Niagara processor, each of these, which is an example of what fine-grained multi-threading was before sort of GPUs, each of these columns are still independent. You can still have different opcodes that can read from different registers. They're still truly NIMD. But I can issue multiple instructions from that one thread in that same cycle. So if I have enough independent work in that one thread, because there's, I've extracted it through my out of order engine or whatever, or even if it's in order, you could still have enough independent work, then you could fill all 4 of those lanes, and they don't have to be the same opcode. If you're looking at this and thinking like this is a GPU, that aspect of it is not GPU-like, right? The GPU, these would all have to be the same operation in order to actually use them all at the same time, okay? Now, it would look like this if you had what? So GPU, so let's say I had a 4-wide GPU, okay? And it's fine-grained multi-threading over 4 different warps. Let's call the warps 4 wide. Why might I have holes like this in the GPU? Yep. Control flow divergence could cause this kind of hole, because some of the threads in that warp want to do this add instruction because they're in the if branch, and the other 2 threads of the warp don't. So I have to turn off the lanes. Okay. So this diagram, if you want to interpret this as a GPU, you have to change the assumptions versus what a traditional fine-grained multi-threading CPU does. Because fine-grained multi-threading in Niagara, which is the Sun processor that's sort of famous for, having a commercially viable-ish product that did fine-grained multi-threading, it was still MIMD. Okay, it was still every lane could do something. Well, every execution unit could do a different instruction. It's just that on the same cycle, you had to issue from the same thread, not from different threads. But that's what hyperthreading gives you, that sort of flexibility. Okay, good question. Other questions here?
And we can also have something in between SIMD and MIMD, right? Where if two of the instructions in the walk are
Right.
turned off, you just put instructions from another walk in there.
So you could do something like that, but that's complex. So there's research papers that do that kind of thing, try to fill it. In practice, it's sort of been too complex and not enough of a win to implement, but we're all clever in here, right? You can find different ways to try to make use of that empty space, and that is one, but it does complicate the hardware to allow for it. Okay. Other questions here? Yeah.
Instead of using like the idea is that can we use like different instructions from the same?
Yeah, you could, but again, if they're not the same opcode with the same register identifiers, then you need additional circuitry to allow different parts of your SIMD unit to do different things than other parts of your SIMD unit. It starts to look not like a SIMD unit anymore. It looks like some quasi SIMD units, right? Where sometimes it does all the same operation, and sometimes you can make part of it do the one thing and part of it do another. Your point is like it doesn't have to be another warp, right? You could basically do the if and the else at the same time, right? In the same warp, if you had this flexibility. Because I could say that the first two warps want to go down the if, they need to do an add. The other two warps want to go down the else, they want to do a subtract. If I had the flexibility to switch the opcodes and switch the registers, then I could have them both use that instruction or that cycle, right?
And identify a similar operation that's happening.
Yeah. So you're Millen's student, right? So we did a paper. Well, one of his students carried forward a paper on this. Like, can I use a compiler to try to do stuff like this and like group similar operations together and like reform them to try to make them better for SIMD? And then if we change the hardware to give you this flexibility, what's the win? So you can do it. You know this, right? Weren't you in the prelim for that guy? Okay, it was before your time. Okay, yeah. So yes, this is doable, but at this point, it hasn't gone out of the realm of sort of academic research. But yeah, you can do interesting things in compiler, and there's probably even more opportunity beyond what Kulkarni's group had exploited there. But that's a good point. Other questions? Yeah.
Suppose let's say there's a control flow dimensions and then by an else, and then else pass needs to be installed. So how will be scheduled? So can it be like the first difference can be scheduled in the cycle one and then some other user work in the subsequent pages and then later there's going to be scheduled?
So cover some of the latency of the if pass with the else path. It's doable, but it's tricky. So we'll talk about, and you watched the video on control flow divergence on the stack, right? So if you wanted to do something like that and allow, cover the execution down one, part of the control flow graph with part of the other control flow graph, and not just switch right as soon as the other one is done, you basically need the ability to schedule from more than just the head of that control flow stack. And we'll talk about that when we get to the next one. But it's doable. You just have to be careful. Okay. Yeah. Other questions here? Okay. All right. So this is roughly what GPUs do. So then warps into blocks, blah, blah, blah. Yeah, the point of all this is that, it's sort of like, because we've got parallelism expressed in the most simple possible way, we can, you could take if you take data parallelism, you can take anything that's vectorizable and you could just make each lane of the vector a thread, right? It's trivial because you've already defined parallelism across the vector. So you could also just make threads instead. This MPI does this kind of thing, right? So if I have data parallelism in my program, I can cut it both up into SIMDs as well as multiple SIMDs. And that is exactly what a GPU does. Okay, it cuts the SIMDs up in the width of a warp, and then it has multiple of those SIMDs that it's running at the same time that it covers on a fine-grained multi-threading basis. And so the execution model from the programmer's perspective, the CUDA code that you're writing is NIMD. So this is scalar. We like to call these sort of a scalar representation because what each thread can sort of go wherever it wants, but then in the hardware level, everything is put together. Okay. And then we talked a little bit about how things get broken down in blocks and warps, and how the warps themselves actually end up getting scheduled on each SM. So we mentioned from the previous part that you can have multiple blocks on each SM. Every SM is going to be packed with a whole bunch of warps. And then on a cycle by cycle basis, you're doing fine-grained multi-threading to pick which warp actually gets to go into the pipeline next. And how the machine does this is not up to you. It is completely, managed in hardware. This is nanosecond scale level decisions, right? This has to happen every cycle to decide which warp is going to get its chance. And the way the machine decides is relatively complicated based on heuristics and changes over time. This sort of algorithm of the individual cycle by cycle scheduling is proprietary. Okay. Questions on this? And you had a question in the quiz about like, okay, on one cycle, can I do an instruction from one thread block? And on the next cycle, do an instruction from the next? Yes. The issue level scheduler does not care. As long as there is an instruction whose dependencies are satisfied, I can issue it into the pipeline. And that's how it keeps everything busy. Okay. Yeah.
Don't we have enough outstanding warps that warp scheduling shouldn't really matter?
You have enough outstanding warps that warp scheduling should not really matter.
Because we don't really care about the latency of the warp.
Right. So the schedule matters if the order you issue the instructions has other effects on the system. Like what other effects on the system could that have? Yep. How much memory bandwidth you need? If I'm doing a bunch of loads from one warp, the instantaneous bandwidth is going to be higher than if I'm just doing loads and adds. It's heterogeneous. What else? So his point is, and it's a reasonable one, if I have enough warps, can I just, it doesn't matter what the issue schedule is because I don't care which warp finishes first. I just want them all to finish. So then the question is, like, why would this matter? Why would the order in which you choose to issue the instructions actually affect the overall runtime of the system? And I had said that basically there's other things that happen based on whatever schedule you pick, one of which was your immediate demand for memory bandwidth. Yeah, right here.
It's kind of off that, like, I guess since there's like specialized like floating point units and like load store units.
Yep.
If one warp, all the threads are using one of the units, then like all the other units are kind of useless.
Right. So you want to try to balance, like there are points in your program where everyone wants the same thing. And if you demand a more intelligent schedule, you could smooth that out, right? So they don't all want the same thing at the same time. And then you're stalled, right? Because you could sort of pack it much more efficiently. Yeah.
Also, the warps may not be independent, they might be dependent.
There may be synchronizations happening here on warps in the same thread block. So they may, scheduling from one thread block. You may want to, because they hit a sync point and then that warp all of a sudden is not schedulable. Maybe you were better off not scheduling from that thing. So you have more instructions to cover the latency of the instruction that's later on. Locality is another thing. So cache misses, right? If I do have locality in my program, the order in which I issue these instructions matters because if, let's say that each thread has, it's like more like a CPU thread where there's going to be redundant accesses from that thread. If I try to fill all of that into my cache from every warp at the same time, there's contention. Whereas if I didn't and I spread it out so that this one used the cache first and the other one used the cache second, that contention would go away. So there's all of these second order system effects that are directly influenced by this issue scheduler. Okay. And so that schedule matters. And there are, if it's graphics, it'll do a different thing. If it's compute, it'll do a different thing. It may be that for some games, it does a different thing than another game because of the way the game behaves. Like you can get driver updates for, NVIDIA drivers, et cetera, that will have like game specific updates for different elements of the system stack, some of which may even be the issue scheduler if that's better. Yeah.
So from like a programmer perspective, like if I write a good program, yeah, that's like a bunch of loads in a row and then a bunch of like execute statements, but they're independent.
Yeah.
Will I have to care to kind of like interleave them, or am I just gonna know that the compiler's gonna like?
So it depends. You can make the compilers like a lot more easy by manually hoisting them yourself, not having registers that might, or not having memory addresses that might alias, right? So the compiler will do everything that it can. As soon as the compiler can't say something for sure, it has to give up. Okay, so generally when you write code, you can trust the compiler, but the compiler can never produce a piece of code that is wrong. That is its number one goal. And so if you're touching memory at all, and a load and a store might have the same address, it's got to make sure that you actually keep the existing order, then you can't move things around up above, and basically it gets hamstrung by things it doesn't know at compile time. So generally, if you know that, this is why we call things const, right? This is why you should use a const modifier, because then it tells the compiler, look, I'm going to read from this thing. It doesn't matter when you read from this thing, it's always going to be the same value. So now I can put stores in any order I like because I don't have to disambiguate the memory addresses. Okay, so you can make a compiler's life easier, and that is a factor. And even in this simple program that we go through in matrix multiply, we make the compiler's life easier by essentially storing the partial result in the register explicitly by creating a local variable instead of just writing out to the array every cycle, because the compiler can't disambiguate the memory addresses, so it has to do the stupid thing. So you can do things to make the compiler's life easier to make your code better and have more independent work. Okay, that's a good one. Other questions, comments here? Yeah, no?
Later.
Okay. Yeah, so anyway, okay, backstory here. I got my PhD, 60% of it was like playing with this. Because it made a big difference in a lot of different workloads. You could do all kinds of interesting stuff. So like the algorithms you use for this issue level scheduler ends up, mattering enough for, a whole PhD. Maybe not so much anymore because it's sort of mined out, but yeah, and it's proprietary. Okay, let's move on to the execution model. Now this is fundamental. Okay, it's issue scheduling algorithms. This is all fine and good, but like you really do have to understand how this works. This is how your code is going to get executed by the machine, how it takes that MIMD program you wrote where you didn't really know about warps at all, right? It just sort of looked like a normal multi-threaded C program, and then it turned it into synthetization under the hood. And this little piece of code is an example of control flow divergence, a very, very simple example where we can see that over time, in the beginning here, things are going really rosy and, the machine is fully used. If I had 4 threads on a 4-wide machine, I hit this if else, half of them go one way, half of them go the other. So then on these 2 cycles, I have 50% of my machine unused, which is really inefficient. And then at the end, it all comes back together. Okay. This coming back together business is actually instrumented by the compiler. I don't know if we mentioned this in the video. Do we? Okay. What's it called? What's the come back together point called? Compiler person. You guys have heard of control flow graph, right? Most folks take a program, you turn it into basic blocks, you create edges between the basic blocks. Basic blocks are just basically, if there's a branch, you go to any basic block, which is going to split off. Okay. You also create a new basic block, and you have 2 places that can come in. There's these sort of rules. What is it in this program? Here, I can sort of see that, they might go off and do different things in the if else, but I can say deterministically, without any question, that they're all going to do E. What's that called? Yeah. Immediate post dominator. Okay, you knew this, right? I'm sorry to pick on you. I just know you do compilers. Did we say that in the video? Immediate post dominator? Yeah. So basically, the compiler is able to sort of analyze the code statically and insert these immediate post dominators in there, so that way the hardware knows when it waits for all the warps to all the threads to essentially come back together. Okay. And so 2 things happen here that are really bad. One is that on these two cycles, you're only using half the machine, and you've serialized the execution because you had to do one path first and then the second. Okay. Questions on this? Is this clear? Okay. Yeah.
Why don't we just call it control flow conversions?
Call what? The immediate post dominator?
Yeah.
No. The immediate post dominator is like a decades old term. It's very precise, right? It's like a graph thing. Like every graph has a post dominator, or you can do post dominator, immediate post dominator analysis. It sounds actually I think it's kind of a cool term, like dominating. That's what. Yeah, but the control flow divergence is a GPU thing that's sort of come out in the last decade or so. Post dominators have been around forever, as old as compilers themselves, as old as graph processing itself, actually. Any graph has dominators, post dominators. We just use them for something usable here. Other questions here? All right, let's see. Right, and then we talked about branch divergence. If that was an answer to a quiz question, then you got it. You already maybe flashed the answer. And then this was speaking specifically to the problem that we looked at the beginning of the class with the quiz, right? Of like, if a whole warp is going one way, then you actually don't experience this problem. But if part of a warp is going one way and part of a warp isn't, then you're in trouble. Okay, so yeah, and threads, like, what is a thread? NVIDIA loves, and anyone who builds a GPU loves to claim that a SIMD lane is a thread, but it's not really a completely independent like lane of execution like people think about a thread. It's really just like a SIMD lane in reality. So you don't really have that many threads when you're running on a GPU. But marketing wise, you can squint a little bit and twist the truth enough to say they're threads, and that's essentially what happens. Okay. Questions on any of this stuff? Yeah.
Has there been any other technical approach other than just like masking?
In research, yes. We will read some papers on this in this class, actually. There's probably on the order of 600 papers-ish that have looked at like, oh, this is a problem on GPUs. How do we solve it? A lot of them boil down to some degree of reshuffling and splitting the work, right? So that you can try to get more stuff to go the same direction and alleviate the problem. In practice, some of this is actually implemented in software. So there are software layers that will do this if it can be done. Other hardware mechanisms that try to reform these things together, only in academic circles. Nothing's been like taped out as far as I know. Okay, good question. And we'll study this like when we talk about some of the work in that space. Okay, other questions here? Is that the end of what I asked you to do? It is? Those of you who read the videos? Okay. Now, let me see. So I think we do this, right, in the video. Do we talk about matrix multiplication at least a little bit? No? All right, let's talk about matrix multiplication, which is today the primary reason for GPU's existence. So let's start at the beginning. Okay, who's written a matrix multiplication function in C before? Probably at least half of you, or if you haven't, you probably could do it, right? It's like on a CPU, right? It's pretty sort of straightforward operation. This is the bare sort of minimum, first cut pass at how I would implement dense. So I'm going to take one dense matrix and another dense matrix. I'm going to multiply those two dense matrices together. I'm going to produce a third dense matrix. And then in this example, I'm assuming that they all have the same dimensions of width. So square matrices, square matrix by square matrix, ending up in another square matrix. If you do this on a CPU, you end up with a triply nested loop. Okay, essentially you have to go through, for those of you who, linear algebra, we even make you take a linear algebra class, right, in grad school. You know what matrix multiplication is, right? You have to basically compute every point of the product matrix. Every point of the product matrix is, basically taking the dot product of a row and a column from each of the two matrices that you're input from. Okay, and you read these in, you sort of do the dot product there, and then you get the end result, and that's what this loop does. So the outer two loops will basically go through all of the output. You think of them as pixels if you want, right? In the output matrix. Okay, it's going to go through each of these in whatever direction you're sort of moving the indices. And then this inner loop is then sort of going through each of the Ks to do the actual, the dot product of those two B vectors. Okay. And what this does is it just reads from M and N, and then it multiplies them together and aggregates it into this sum thing. And then once we're done with whatever the product value is, right, we just write it out to the end product matrix here with indices. Okay. Straightforward. This is how you do this if you're doing this on a CPU. Problem is ripe for tiling. It's also ripe for parallelism, right? As your matrices get bigger, conceptually, you'd have more product output pixels, so you could run those on more threads. That conceptually is essentially running threads across the two outer loops, right? So you can take those two outer loops and then parallelize them across all of the cores on a GPU, and then each individual core is sort of running through each vector and then doing the math. Okay, questions on this? Basic matrix gems. So we're going to start with this, and we're going to show how we turn this into CUDA, and then we're going to show how we optimize it. And we're going to go deeper this year than we have in previous years. I'm going to, after we sort of go through the basic optimizations, you're going to have to do this. You're going to have to code it up yourself in CUDA and try to optimize it in a meaningful way. We're actually going to, the assignment, I believe, even focuses on, if we basically get you to do the dimensions of AlexNet. Okay, because it turns out that, machine learning boils down to gem operations, and you can implement kernels yourself in CUDA that implement those gem operations or convolution operations. Convolutions get turned into gems, which we'll talk about, and that's what your assignment's going to be. Like, try to code this up and then try to get it to run fast. And this year, we're going to give you a little bit more help on that front. Talking about how you transform the thing into a gem, talking about tensor cores in more detail. So hopefully some of you will actually be able to use them this year. Okay, that's the forward pointer to like the piece de resistance of the final CUDA programming assignment that you guys are going to do here. I think is available now, right? Assignment 2 is out. There's 4 parts. What did we get to do you to do in 2 again? Do you remember? You don't remember. No one's looked at assignment 2 yet. Okay, you're still in Blur. It's going to end with matrix multiplication, okay, and optimization to matrix multiplication. All right, so here's your host program. This is the exact same thing I showed you before. Yes, it's right for tiling. Okay, so how are we going to tile this? So let's take a very simple example and illustrate how tiling is beneficial to this program in terms of how much reuse you're going to be able to exploit here. So here's a simple example where I've got a 4x4 matrix. And I'm just going to conceptually break it down into 2x2 blocks. This holds generally as we get to real sizes, but it's much easier with just smaller sizes. So I am going to tile them together such that there's 4 product elements going to be computed in in each block. Okay, this is the work assignment. So questions so far? Hopefully, small matrix. 4x4, of which I'm doing 4x4 tiles of each of the products. I can make this bigger, right? And then I can keep the block size the same. So here I've got a width of 8, and then tile width is also 2, and then I can cut this up into more blocks. I could also just make the blocks bigger, right? And I could do the same thing, but now my blocks are larger. Okay, these are the different ways you can sort of cut up this problem size. And you have the flexibility to play with this if you're sort of writing your CUDA kernel. This is effectively how big your block sizes are, within some limits, right? Once your matrix gets super big, if you have a 1,000,000 element matrix, you can't have a 1,000,000 thread blocks. Like you can't have 1,000,000 thread block. You can only make them at most 1024 threads, right? So then the only way you scale is just by having more thread blocks. Okay, so you can sort of take this and you can tile it in different ways, cut it up in different ways, etc. So here is how we would launch such a program from the host. So you define your dimensions, and this is similar to what we've done before, but now we're explicitly sort of like having this tile in here. And this tile is relevant because the tile is going to matter when we start to load things into Scratchpad. Okay, we're going to conceptually tile it so that the stuff that we load in is going to be stored in some intermediate storage, which is your Scratchpad, and then we can exploit the locality in that tile in the Scratchpad. Okay, for the very simple kernel, we're not going to worry about that Scratchpad just yet, but this is sort of how you would invoke it. To write the kernel itself, you guys have sort of done this enough that this is hopefully pretty straightforward. It's going to be a global function. And what's important here? So it's going to be a global function. And one thing that we do have to point out is that we are going to explicitly create an intermediate value for the partial product. So p-value equals 0 here. Why is that? I mentioned it earlier in the class. So this thing is incremented inside the inner loop. Why do I want to say float p-value equals 0 here? Yeah, to ensure it's allocated to a register. If I do not do this, and I just go straight to the right, because ultimately I'm going to create a partial product, and then I'm going to write it out in global memory in the output matrix. If I do not write this line, and I basically just store to the output matrix inside the inner loop, this is one of those instances where you've like kicked the compiler in the shins, because that's a store instruction, okay? And the compiler doesn't know if that store instruction is going to store to any address that you might be loading from when you're in your inner loop, right? So in your inner loop, you're loading from M and you're loading from N. That's how you get the data to do the dot product. If you then immediately store to some place in P, at compile time, the compiler doesn't know that they don't alias. Compiler doesn't know that your pointer to P isn't the same as your pointer to M or your pointer to N, which means that it has to store it before it does the load on the next iteration. So you can't get rid of the store. So then if you left it in there like that, then you're going to have load, add, store inside that inner loop, and you're going to do that for the entire dot product. If you did this and you were explicitly saying, I'm not writing this out to memory, this is a local variable that only my function cares about, the compiler is smart enough to say, I'm going to put that in a register. Like that sounds like something that's good for a register, and it will do it. So now in your inner loop, you'll do load M, load N, add, and then store in a register. And then once you're out of your inner loop, you can then write it out and do the store. So you avoid all of these extra stores that you would have to do. You would have basically width times more stores in your program if you didn't do it this way. I think there's a question on Piazza about this as well. Does that make sense to everyone? Okay, good. So again, this is an example of how you can help your compiler out. You can also tell your compiler that these things don't alias. There are special keywords in most program and most compiler backends to say, I think restrict. I don't know what it is in CUDA actually. There's a keyword you can put in front of pointers to tell them that they don't overlap. So then it could do this for you. But it's usually easier to just create the local variable than like mess with pointer definitions. Okay. All right. So how does this work conceptually? So let's think about the amount of data that we load and the amount of data that we use. So I'm going to go back to my very small block, my little 4x4. And I'm going to, think about this from the perspective of the output pixel, let's say, or the output element. What do I need to actually compute each of these elements? Let's go here. So basically, if you look at this sort of math on how you compute the row and the column, this is very similar to what we've done before. But conceptually, you have to read all of this and then all of this to compute this particular element, right? And then to do this element, I have to reread all of this and then read all of this anew. So there's locality here, right? To do the adjacent element, I had to read the same row as the element to my left. The same is true up and down, okay? I had to read the same column as the element above me. If you do not use the Scratchpad in this example, what's going to happen? Damn, it's going to be a problem. You're going to have redundant accesses to memory. You're going to have one element, performing loads to your main memory system that is going to load that whole row of M and the whole row of N. And then the other element is, if they're in the same warp, it's not that big of a deal because it actually has mechanisms to collapse them. But if they're not in the same warp, then it does it on distinctly different instructions. And that's going to suck bandwidth either from your cache if you're lucky, because you'll hit in the cache because it'll still be there. If you're unlucky, it'll be been evicted from the cache because all those other thread blocks you're running are also doing the same thing and sucking their rows in and evicting your data. Then you're just going to miss in the cache and you're basically going to not exploit any locality. This is how we sort of identify what can we put into a scratch pad. Is there locality among the threads that we're going to code up on the input data? And there's no problems on collision of the output here because conceptually each thread is pushed into a different element of the output. Questions on this so far? All right, how does this move? It moves intuitively. So next block will do a similar thing. Okay, so this block is now also going to read those same two columns because it has to by definition. And it reads it reads the same two rows of M in this case. And then it reads, a sort of fresh amount of N. And then we sort of go through you sort of go to every quadrant here, right? You do this, and then you can sort of see where the redundant axes lie as you sort of move across M and N to produce P. This is the code for the kernel, okay, for the very simple gem kernel. And the first time people code things up in CUDA, this is what simple matrix multiplication looks like. You compute the row and column in the same way we did for all of our other two-dimensional data. You turn that inner loop. You have to keep that inner loop around. Okay, the inner loop is now just iterating through the output data. And we sort of perform this little caching thing here by putting this in here. Now, if you're looking at this code and you're like, wait a minute, right? So where's the right? The right is right here. I'm sorry for the formatting of the code, but like the for loop isn't actually writing it out every time. The for loop is just doing the inner part of this. It just looks like it's not because we didn't put brackets or there's some formatting like spacing issues here. But that inner loop is only performing the increment to p-value. Okay. So this is the dead simplest way you can take a gem and you can put it on a GPU. And the performance of this versus the performance of the most optimized version is orders of magnitude difference. It's not like a toy amount of performance left on the table to do it this way. But this functionally works. It just was going to take a long time. Are there questions on this so far? Yep.
I think you were going to answer it, but at what dimensions does it become memory bound versus compute bound?
Yeah, that's a great question. So it depends on the compute intensity. Okay, so we're going to talk about that. There's quiz questions on this as well. But what you're going to be able to do, what we'll force you to do in this class, is look at a piece of code and try to analyze what is its compute intensity. Okay, what do I mean by compute intensity? Does anyone know what I mean when I say that? Yeah.
The number of compute operations in one instruction.
Number of compute operations in one instruction. Not quite. In one line? No.
Yep. So the amount of operations you do for every load.
Yeah. Fundamentally, it's the ratio between how much compute you have and how much memory you're doing. Okay. GPU scale. Okay. So what matters is the rates at which these two relative things are scaling. That really, when you try to figure out what your machine is going to be bottlenecked by, you can do a back of the envelope analysis and say, I know what this single thread does. I know how much memory it reads, and then how much compute it performs. Okay. In this example, we can analyze that. Okay, from the global memory space, let's ignore writes for right now. How many reads are there for every floating point operation that we're going to perform? Can you tell from looking at this? Two. Right. You have two memory accesses, each of which are how wide? How wide is each memory access in a single thread? 32 bits, 4 bytes. Okay. You load two floats. You do this with a CPU program too. It's just sort of less effective to sort of do this analysis because there's all kinds of craziness happening to extract parallelism. In a GPU, you are literally just scaling up this code as you sort of run one thread. So here I am loading two floats from memory, 8 bytes for every floating point. How many floating point operations am I loading to 8 bytes for? 2, right? If we count the multiply and the add as 2 operations. Okay, in reality, those end up being one instruction in machines because it turns out that this multiply and accumulate, this is super common. So you actually want a complex instruction that we call max that does both of those things. But from a raw floating point perspective, I am loading 4 bytes for every one floating point operation in this code. And I'm loading those 4 bytes from global memory. Yes, question.
But you've tiled at least this particular kernel, right?
I have done nothing to exploit that locality, right? I've tiled it because the programming model forced me to tile threads, but I've not tiled data in any way. I have not loaded the data in anywhere that I can exploit that locality. If you have an intelligent memory system, some of the locality will be exploited by the caches. But in GPUs, you cannot rely on that because there's just too much work going on to rely on the caches still having the data in it. So the first step as a CUDA programmer, I tile it parallelism wise to try to like figure out how many threads I need. And then once that's sort of up and working, you get a kernel that has a particular density of compute per bandwidth. And that density is usually crap, right? This is bad, right? Loading 4 bytes for one floating point operation is very, very bad. You want to load less data and have more compute generally, okay? And that's relative to the scales at which we can scale the compute versus we can scale the bandwidth, right? Just fundamentally when we design the system. Question here.
So I guess like I can't understand. So if we're saying that we can't rely on the cache at all, it's quite challenging.
Right.
Why bother having a cache?
Good question. Because sometimes you can. I mean, it's like general stuff, right? Like, why bother having a cache if my program is streaming, right? It doesn't. Some programs aren't. Generally, so this is why in the beginning GPUs just didn't really have any material caching, because graphics, other than the texture caching, which is a little bit weird, super high latency, but it's mostly streaming accesses, so the cache didn't really matter, and you can hide the latency with more parallelism. There are workloads for which the cache may be effective. If you want to make a machine that works for more than just one workload, then you sort of have that. That's what a cache is, right? A cache is like a punt on Scratch. It's like, I don't want the programmer to actually like explicitly encode any locality, so I'm gonna put tags in there so their life is easy. And it turns out that, well, people like that. But you know, if you had an expert programmer and if you could statically figure out everything, there would be no need in life for caches, right? But both of those things are not ever true. Okay, question here.
So is the locality here the fact that if you hold the row constant, you need to iterate through the columns. So pi is basically taking the row out of the cache. Right?
So the way that this parallelism gets exploited, and we'll talk about this when we go to the memory system and think about how these accesses are going to happen. If we look at access to M, okay, M is basically looking at the row, right? So it takes whatever row you're at, which is determined by your Y index, multiplies it by the width, and then you basically, every iteration of this loop, you increment K by 1, okay? So there's spatial locality inter-iteration on the M axis, correct? Because like I access the first block in the cache line on the first iteration, then on the next iteration, K goes +1 and access the next block, etc. That's actually the wrong way to exploit locality on GPU. You don't want that. GPUs actually much prefer the second access, which is somewhat counterintuitive, where every iteration of this loop, I'm actually going to the next like row, right? Because every time K moves on the axis to Dn, I am jumping a whole width. So there's no cache line is definitely much smaller than the width of the matrix. So there's no spatial locality there. But if I look at what I'm adding to it, this plus call business, and I look at the composition of how I got to plus call, it's basically going to result in adjacent threads accessing adjacent data, okay? Which is fantastic for the GPU memory system, because in one warp instruction, I'm actually going to be able to read a whole chunk of data and feed multiple threads, okay? So this is a good example of 2 different access patterns, one of which is good for sort of sequential CPU type accesses, and the other which is much better for GPU accesses. So instead of exploiting the spatial locality between iterations, That second access is exploiting the spatial locality between threads, which turns out to actually be much better. And we'll get into that in a lot more detail as we look at the memory system next lecture. Okay. More time. How was the quiz? Do you want more quizzes? Raise your hand if you want more quizzes. Raise your hand if you want less quizzes.
Bonus quizzes or quizzes?
These are bonus.
Oh, yeah.
You know, your grades are only like part of why you go to college, right? You actually do want to learn something. All right, fine. We'll probably do this again, especially if we have to cancel a lecture or something. That's it for today. We'll plan on sort of normally me going through the stuff on Tuesday. We'll see you then. Thank you.